Assalamualaikum warahmatullahi wabarakatuh, and hi to my students. This is a video lecture for a cyclic subgroup, and also I will add up about the center and centralizer afterwards. The concept of cyclic subgroup, based on the definition, there is an element in the G of group G such that a to the power of n, n is a positive integer, such as element A is called a generator. Okay, quite long. Let's start first with the fundamental of a to the power of n. We start first with a given example of U5 here, and U5 is defined U5 under multiplication. U5 we know that consists of 1, 2, 3 and 4. This time, it is better for us to develop a Cayley table first to see how to do the operation of a to the power of n. 1, 2, 3, 4 and multiply. 1, 2, 3, 4. 1, 2, 3, 4, 2. 2 times 2 is 4. 4 mod 5, 4. 6 mod 5, 1. 3. 3, 1, 3, 3, 9. 9 mod 5 is 4. 12 mod 5 is 2. 4, 3, 2, 1. Okay, finish. The concept of how to generate a to the power of n, suppose that 1 is the generator, symbolized like this, and how to find the elements of 1 to the power of n. It's not this really similar with the multiplication of 1 to the power of 1, 1 to the power of 2, 1 to the power of 3. It's like that, but it must be specified to the binary operation of the question. For this kind of question, is binary operation of multiply and then you mod 5. 1 to the power of 1, of course, is 1. Please look at the Cayley table for the answer. 1, 1, 1. How about 1 to the power of 2? 1 to the power of 2 is basically 1 to the power of 1, you binary operation with 1. And this time, 1 to the power of 1 is 1, binary operation with 1. Look at the Cayley table, it still produce 1. And 1 to the power of 3, the same like the previous one. 1 to the power of 2, binary operation with 1. 1 to the power of 2 from the previous step is 1. Binary operation with 1, you still get 1. Therefore, if you repeat this to the power of n, 1 to the power of 4, it will produce 1, 1 to the power of 5, and then it's enough because it will go back to 1 to the power of 1 because it's modulo. Modulo has a cycle. By this pattern, it will never generate any other else except 1. Therefore, it's not really that interesting for the time being. Let's look for 2. Okay, 2. 2 to the power of 1 will get back itself. 2 to the power of 2 is 2 to the power of 1, binary operation with 2. 2 to the power of 1. So 2 binary operation with 2. Based on the Cayley table here, it produces 4. 2 to the power of 3. Oops. Okay, you take 4 binary operation with 2. 4 binary operation with 2 based on the Cayley table produce 3. Therefore, please, it's not similar as usual multiplication. 2 to the power of 3 for usual multiplication is 8. But again, this is for the case of modulo 5. Therefore, it produces 3. We have one more, which is 2 to the power of 4. 2 to the power of 3 is 3. Binary operation with 2, based on the Cayley table, it can be seen that 3 binary operation with 2, you get 1. Okay, let's try to extend this thinking into 2 to the power of 5. And why will it repeat itself back? 2 to the power of 4, binary operation with 2. 1 binary operation with 2, you get 2. If you continue this for the 2 to the power of 6, it will produce the next 4. 2 to the power of 7 will produce 3. You can verify on your own. 2 to the power of 8 will be 1, and then the cycle repeats itself because this is modulo. It's enough for you to stop until 2 to the power of 4 because, like I said, it will repeat itself back. Therefore, the generator of 2 produced by the order of the solution 2, 4, 3, 1. Okay, it will produce every elements in U5 back. If this kind of generator exists, generator must produce every element, and 2 produce every element of 2, 4, 3, 1, not in order, because this is a set. It can be not necessarily must be in order. 2 is the generator. As there exists a generator inside this U5 under multiplication, U5 is cyclic subgroup. That's why U5 is a cyclic subgroup, because there exists a generator, at least one generator, and the generator is 2. And 3 is also the generator. You can verify it on your own. Still enough conclusive proof to show that it is a cyclic subgroup. Let's try to verify why U8 there is not a cyclic subgroup. The basic explanation is that it is not a cyclic subgroup because there is no generator. In order to prove that there is no generator, you must try for every element inside U8. Okay, let's define G here is U8 multiplication, and U8 consists of this all elements inside which is relatively prime with 8, 1, 3, 5, 7, or are relatively prime because the GCD is 1. And then it's better for you to do again the Cayley table. 1, 3, 5, 7, 1, 3, 5, 7, and binary operation. 1, 3, 5, 7. This is mode 8, 3. 9 mode 8 is 1. 15 mode 8, 7. 3 times 7 is 21. Mode 8 is 5. Okay. 5, 15. 15 mode 8, 7. 25 mode 8 is 1. 35 mode 8 is 3. This will be 7, 5, 3, 1. Okay, let me double check. 7, 20, 21, mode 5, 35, 35, 32, 3, 49, 48. Okay, this one. Okay, our Cayley table for U8 is finished here. Let's try again by the previous concept 1. Let's check whether 1 can generate every element inside U8, which is 1, 3, 5, 7. 1 to the power of 1 is 1. 1 to the power of 2 is 1. Binary operation with 1 is 1. Okay. 1, 1 is 1. 1, 3 is 1 to the power of 2. Binary operation with 1. You take 1 here. 1 binary operation with 1 is equals to 1. 1 to the power of 4. You might know the answer already. 1, 3. Binary operation with 1. You get 1 binary operation with 1 equals to 1. Therefore, 1 can only generate 1. It cannot generate 3, 5, and 7. Let's verify for 3 as well. 3 3 to the power of 1 is obviously 3 itself. 3 to the power of 1 binary operation with 3. Okay, based on Cayley table here, 3 binary operation with 3 will produce 1. 3 to the power of 3 is equivalent to 3 to the power of 2 binary operation with 3. 3 to the power of 2 is 1, and 1 binary operation with 3, you get 3 back, and you can see a cycle there. This one. Okay, therefore 3 can only generate 3 1. You can carry on this thing for 5 and 7 as well, but unfortunately 5 can only generates 5 1. 7 can only generates also 7 and 1, because there does not exist a generator for U8 under multiplication. You can say definitively that U8 is not cyclic. Very simple. The important skill that you need to have right now is how to generate a to the power of n. You need to check for the generation of the element whether it can produce every element of the given G. If it can produce every element in G, therefore it is known as generator. And if generator exists in G, therefore G is a cyclic subgroup. You can check for other kinds of G, be it Z plus, Zn and Zn star, and also for this kind of example is Un. If it can have a generator, therefore it is a cyclic subgroup. Let's look for a while for the concept of center and centralizer. This one is very simple. Okay, the definition of center. Center is defined as Zg, not that Z integer, Zg. Okay, Zg, this one. Is a set of elements that commute with every element. You know the concept of commute already. Later I show you. I write again the centralizer. Centralizer Cg A, and the A is in a given G, is basically an element which commutes with every element in a given G. Okay, we start first with the recap of the definition of commutativity. Commutativity means that for every element in G, for every A, B in the given G, this happen: A binary operation B equals to B binary operation with A. As simple as that. That is the definition of commutative. However, for this concept of center, okay, let's look. For the previous example, there is an example on the left there, but it's not a defined G. You can use back for the concept of U8 just now under multiplication, the previous example. Okay, give me some time to develop the Cayley table back. 9 mod 5, 9 mod 8 is 1, 15 mod 8. 3 times 7, 21. Is 5. 5, 15, 7, 25, 1. Okay, 7, 5, 3, 1. Okay, finished. And let's try to find a center for this case. The center for this case, okay, let's look for the centralizer of 1 first. U8 consists of 1, 3, 5, 7. It's very simple. You just need to check 1 commutes with which element. Okay, based on the Cayley table, let me use a different ink. 1 commutes with 1 because 1 binary operation 1 is equal to 1 binary operation with 1 is equal. 1, 3 is equivalent. Okay, let me use a mouse here. 1 and 3 is commute with 3 and 1. It's similar. Okay, let me write it again. Show you one by one. 1 binary operation with 1 is equal with 1 binary operation with 1. 1 binary operation with 3 is 3. Commutatively, 3 binary operation with 1 is also 3. How about 1 binary operation with 5 is equal to 5 binary operation with 1. 1 binary operation with 7, there is 7. 7 is commutative to 1. Therefore, CG1 commutes with itself 1, 3, 5 and also 7. Basically, every element in U8. Okay, let's try to look for the other one. CG3. Again, the simple thing, the similar thing. 3 commutes with 1. You check 3, 1, you get 3. 1, 3 is also there. 3 and 5. 3, 5 produce 7. 5, 3 also produce 7. 3, 7 is 5. 7, 3 is 5. And I forget itself. 3 binary operation with 3, obviously yes, 3 binary operation with 3. Again, CG 3, 1, it commutes with 1, itself 5, 7. Again, the centralizer for 3 commutes for every element, and you can repeat these steps. For CG 5 as well, it commutes with every element. If you can verify it on your own. The thing is that you must know how to read the Cayley table again. And CG7 is also 1, 3, 5, 7. And as centralizer of 1 is the G itself, also applies to 3, 5 and 7. The definition of center back. Center, it means that an element in a given G that commutes with every element. Therefore, there are multiple center inside this example of U8. The center for U8 under multiplication can be 1. 1 is a center. 3 is also happens to be a center, commutes with every element. 5 is a center. 7 is the center. Let me show you another small example, perhaps, to show, to make us more understand with this concept of center and centralizer. Okay, this time let us to recap back, Z3 under addition. And you know that Z3 consists of 0, 1, 2. Again, I need to refine back what is the definition of center in the English. Element which commutes with every an element. There is a center. Center is a set. Centralizer is a set of element which commutes with A. Okay, let us start by developing a Cayley table for Z3 under addition. 0, 1, 2, binary operation, 0, 1, 2, 0, 1, 2. 1, 2, 2, 1 plus 2, 3, 3, mode 3 is 0, 2, 0, 1. Okay, let's again look for the centralizer for 0 first. Again, the same principle, you check whether 0 commutes with 1 itself first. 0 of course is 0, commutes with a 0 binary operation with 0. And 0, 1. 0, 1 is 1 and 1, 0 is 1. Therefore, it commutes with 1. And 2. 0, 2 produce 2. 2, 0 also produce 2. Okay, it's clear here that the centralizer of G produce 0, is commutes with 0, 1 and also 2. Okay, let's do for 1. And if you look there, 1 commutes, from the previous example, 1 commutes with 0. It commutes with itself, of course. I want to only check for whether 1 commutes with 2. 1, 2 is 0. 2, 1 is 0. Okay, definitely 1 binary operation with 2 is equal to 2 binary operation with 1. Okay. And let's finish our step for the centralizer for 2. As it commutes with 0 just now, it commutes with 1 and also it commutes with itself because 2 is 1, 2 is 1. For the center, again the same conclusion with the previous one. The center is an element which commutes with every element in the given G. There are multiple center right now as well for Z3 under addition, which is 0 is the center, 1 is also the center, 2 is also the center. Okay, I found out that based on our most example in this chapter, almost every Zn only Z plus don't have a center. Okay, it still have a center, don't have a multiple center. Okay, I show you again one more. Let me clear this. Okay, I always talk about Zn, Zn star and also Un. Why not this time I involve an infinite set of Z, not N, Z only plus. When you try to derive this addition of integer, you must know that integer consists of infinite numbers, including -3, -2, -1, 0, 1, 2, 3, and until a very large integer. Okay. Is there a centralizer or even a center here? Okay. 1. Suppose let 0 be the center. Okay, or I can say I start with the centralizer first. The centralizer for G 0. Okay, 0 commutes with what element? 0 plus 1 is 1. 1 plus 0 is 1. Therefore, 0 commutes with 1. Okay? Let's try 0 plus 2 is 2. 2 plus 0 is 2. If you continue this pattern, the centralizer of G will be every element in integer. Okay, let me delete this. I cannot delete this. Oh, apparently I cannot use this example because it commutes CG also. Of course, 1 plus 0 is equals to 0 plus 1, 1 plus 2 is equal to 2 plus 1 as well. Okay, we scrap this example. Again, it's a multiple center there. Maybe I change the question to this one. Okay, this one is fairly simple. Subtraction of integer. Okay, this one you will see. Okay, let me show. CG for 0. Okay, 0 plus 1. Hey, plus pula. Minus 1 is negative 1. 1 minus 0 is 1. 0 minus 1 is not equal with 1 minus 0. Therefore, 0 is not commute with 1. 0 does not commute with 2. 0 minus 2 is not equal with 2 minus 0 as well. 0 only can generate, not generate, the proper word is it only commutes with itself, with its 0. Okay, how about for centralizer for 1? 1 minus 0, okay, 1 is not commute with 0. Let's try this one. I do the scrapping here. 1 minus 2 is negative 1. 2 minus 1 again is 1. 1 minus 2 is not commutative with 2 minus 1. I think the pattern remains the same. Okay, 1 only commutes with 1. Centralizer for 2, only 2. As you can find here, okay, this is the centralizer for 0, 1 and 2, and I don't expect you to do for every integer, of course, but again, I want to conclude here that there is no center for the subtraction of integer, because if you do the find to find the centralizer, there does not exist an integer which commutes for every integer for the case of subtraction. I hope you find this lecture useful, and if you don't understand, you might ask me back or Madam Anis. Thank you so much. See you for the next video, and goodbye.